So cool. So when we last spoke, right, Tuesday, we went through a bunch of different data types in Python, right? The ways Python represents data, or the way Python arbitrarily just like represents things we might need to interact with in our code, right? Some of those are numbers, right? Numeric types. We had um, the integer, we had the float. We also had the string, which kind of represents arbitrary text. We had Boolean, which is one of two values, always true or false, and kind of used to represent the output of conditions. And we also had the none type, which is capital N none. Its value is used to represent pretty much the absence of data, usually, um, while still fulfilling Python's desire to like have a thing to reference and latch onto. Um, we also saw, right, methods and functions a little bit, right? At least some of what's built into Python. And so from then we can continue on a little bit and introduce some new behaviors and some new types today, which will be useful to us. So just quickly in review, right? We can define a new name if we want a variable name using the assignment operator, what we formerly called the equals sign, but which is now just the assignment operator. Um, And we can use that operator to take a thing on the right, assign it to the name on the left, right? Again, this is the Boolean value, capital T, true. Um, we can do this with, any name we create in pretty much any type or value, right? This is the integer value 12, right? Which again represents the number 12. We also have, other types, right? For example, we have floating point number, right? Again, the second numeric type, which is similar to an integer but has a decimal, right? Has some precision after the one place that we can use to help us, right, just represent more precise numbers. So we're going to start now looking at how we can make our code more dynamic, right? Last time on Tuesday, we really just had a text file that was a bunch of lines that all happened top to bottom, and then that was it, right? Our script couldn't do anything complicated. It just did math top to bottom. We could print stuff if we wanted to, and then it ended. Obviously, in you know programming, you frequently need to execute different code under different circumstances. So we're actually going to jump into one of the first ways we can do that. So we're going to start looking at control flow. Control flow is really looking at how to control which pieces of your code execute in which situations. All right. The most basic keyword to implement some control flow in Python is if. All right, so we can start off with if, and if takes some expression to follow it. All right, so we can say if our number greater than 10. This, fortunately for us, reads a lot like English, right? If our number is greater than 10, I'm just replacing the operator or adding, right, an is in between these two. Then we can run some code, right? In this condition, we can run some code. So we can print let's print the number is too large for now. When I have this statement, right, the way if works is if will evaluate whatever expression follows it. If that expression is true, we will run its associated code block. And in Python, we'll see this relatively often in a scenario where we would like to associate generally speaking, right, if this statement is true, again, we'll run this and we'll see there's a colon here, right? In the event in Python, we want to associate code with some other block of code above it, right? For example, we want to associate the if with like the code we run under the if condition. This could technically be a million lines long. If we wanted to, Python usually uses a colon followed by indentation. All right, this is how you can tell Python this line belongs to this condition and statement right here. So if I run this file, what do we think is going to happen? Any takers? What do we think is going to happen here if I run this? Are we going to get any output? Are we going to get no output? What is the expected behavior, you guys? All right, we got no takers here. There we go. So I think nothing's going to happen, right? So Paul says nothing is going to happen. Marcus also said it won't print anything. And that is correct, right? We run this script, nothing happens because this condition is not true, right? 0.905, right? Less than 1 is not certainly greater than 10, so nothing happens here. We can always, right, make it work, for example, by getting rid of this dot and making it an integer. Now we get this print, right? The number is too large. Awesome. So we can use one condition with just if, right, and then continue on with our code. But if frequently has another partner in crime, right? There's this else, and we can use else to sort of marry some default case to our if statement, right? Every else needs an associated if statement. And the way this works is, notice else, right, is unindented. So obviously it's outside the realm of if's control flow, but it's they're associated strongly with each other. Else takes its own logic. And the way this works is, in any if-else block of code, only one of these two is ever going to happen, right? So if we print here, if the if triggers, Python will skip the associated else, right? When I say associated else, that's just the next else after it, right? Assuming there's no other code between them. So in this scenario, we're either going to say, if this condition is true, we'll print this. If this condition is false, we'll now print this statement instead. And that will give us, the ability to run sort of an either or type scenario with our code, right? Now, if I run this, we get the second print statement. The number is just right. But if I change our number to be, again, greater than 10, we now get only the first print statement, right? This number is too large. We can start with two conditions, right? This is relatively useful. Python has a third keyword we can use as well that will let us add sort of this arbitrary, any other number of conditions we want, just in case. So for example, I can use the elif statement, which basically is a shortened version of else if. And it can take an additional condition. So we can add as many conditions before else as we want, right? So we can have if our number is greater than 10, elif our number greater than, not greater than, less than 0, where we can print something else. So it's too small. And so we can add as many elif conditions as we want. Technically, any if-else block of code can only have one if to start it off, one else to end it. There's many elifs as we want in between. Right? That's just how the structure goes. This is beginning, this is end, this can be whatever we want, right? We could have as many weird conditions as we felt our code needed. So if I add minus, right, to invert this, make it negative, you now get this number is too small. So we can continue correctly evaluating everything. Just like with if, right, else will only happen if neither of the above conditions happen, right? These three are all mutually exclusive. we'll only get one of these 3 little blocks of code to fire. By block, it's just 3 print statements, but we get the idea, hopefully. Technically, in Python, in addition, if we want, we can jump to 2 other keywords that might help us for logical comparison. If we look here, if we decide that, I don't really care if it's too large or too small, I'm just going to give you a yes, no output. We can actually chain conditions together here using one of 2 logical operators, the and or operators. All right, so I can clean this up. If, I'll just copy our conditions here. So if or our number is less than 8. And then here we can say, we'll just print something generic, right? The number is no good. And so this we can use again to bring these 2 conditions together, right? Or like we would think in English, we'll basically evaluate either of our conditions to see if it's true, right? If one is true or the second is true, Python will print. All right, as long as one of these 2 is true, we're good. And obviously that's important because these won't both happen at the same time, right? You can't be greater than 10 while also being less than 0. We can still add the same else, right? And then be on our way. Let me comment this out real quickly. And then we can be on our way towards having slightly more, if not even efficient, but slightly cleaner code that's just easier to look at, right? With fewer lines, obviously under the assumption that, the nuance between too small and too large doesn't matter to us. So here we get no good. Here we also just get no good. With 9.05, then we get number is just right. All right, so we can use this together to our advantage to just use conditional statements in a more interesting, more elegant way, and to, again, impact how our code actually runs, which is a nice start here. As you might guess, right, seeing the or keyword, I did mention it too. There's a and keyword as well that's built in. The way the and operator works is basically the opposite of or, right? It will evaluate if both statements are true, right? The statement preceding and the statement after it. So for example, we can just say if 7 greater than 2 and 9 less than 17, we'll print, or you can just print both true. Again, right, we think back to just numbers, right? 7 is greater than 2, 9 is less than 17, so we will expect to get the both true statement printed to our console. All right, so we get this, and we get a nice easy evaluation of our 2 conditions. You can technically, in Python, chain is an arbitrary number of conditions together with and or as much as you want. You can put 8 ors together in case like one of the 8 will be true. Generally speaking, that's probably not a great practice because it'll just get really hard to read your code, right? And no one's going to know what's actually going on if they look at it. But theoretically, it could be done. It's worth mentioning, right? You can chain as many of those together as you would like. Cool. Any questions thus far? Hopefully this stuff is relatively smooth thus far. Again, it does help that Python 2 is relatively English language-like, right? So this reads like a pretty easy to understand sentence, right? If this condition, right, if 7 is greater than 2 and 9 is less than 17, we'll print both true. And it should make sense to us. So we've already seen, right, at least one data type that really can be treated as a collection of, separate pieces ordered together, right? We saw the string. The string can be treated basically like it's a collection of different characters, with the first character being the first and the last character being the last, right? So if we look at it, just type a bunch of garbage out. Right, this is technically to Python, it could be treated as a number of individual characters, right? Starting with semicolon, going all the way to lowercase n. We can't do that much with them, right? We saw a few built-in methods last time, but there's not that much utility otherwise here. But it's an example, again, of something that we're about to see in much more detail with a few other types built into Python. So we can start out with Python lists, right? Python lists are they're not that similar to strings, but they are similar to strings just in that they are, again, a collection. Yep. So question from Marcus. He had both comparisons without the if statement in front. Would it automatically return a Boolean value? So in this case, it would return true without the if statement. So Marcus, you mean if we're not trying to like conditionally run code, but like what would be so like what would example be? Is that kind of your question? If you wrote this statement just out, it does give you back a Boolean anyway, right? So this is going to ultimately give me back example is equal to true. If I print example, it will be capital T true. Right, this expression ends up as true. This expression ends up also as true. True or true is true. So we will ultimately get back a Boolean value. Yeah. Did that answer your question? Cool. But yeah, if ultimately is just taking whatever comes after it and then just evaluating it as a Boolean. Like technically, if 3 will also be true, if string will be true, but with conditions, it's always going to be an actual Boolean value. Cool. So anyway, if you look at lists, right, this is going to be the first sort of compound data type for Python that we can start looking into. The Python list, unlike a string or any of the other data types you've seen, right, they're all kind of homogeneous. Right? A string is made up of string characters. The other ones are just static values. A list is defined with square brackets, and it is actually an ordered collection of different Python values or Python objects, or really just types that we've seen so far. So for example, this is a list, right? It starts with an open square bracket, it ends with a closed square bracket, and has just an ordered collection of anything in Python. The elements can be integers, they can be strings, they can be floats, they can be Booleans, they could be other lists. In fact, they could technically be functions if we want them to be. They can be any type in Python that we would like. Obviously, with the constraint that if we're writing this code, we need to understand how it is going to behave, and we need to know like what to expect in our list. But theoretically, most levels of complication that we could want are valid here. So this is just a simple list, right? We don't have like a list of a list or something. We'll deal with that a little bit later. But a list is ordered. And when I say a list is ordered, what that technically usually means is, the first element is always going to be the first, the last element is always the last, the fifth element is always the fifth element. So all of the list positionally won't change. Python will assume that's important to us, unless we manually try to change it in our list, right? But Python won't just reshuffle it, and we can access the elements by their position if we want. Built into Python, there's another type that's worth mentioning quickly that is called a tuple or a tuple, depending on who you talk to. I say tuple. Python's documentation technically says both are correct. Some people say tuple. You can pick whichever one you think sounds snappier and use that. Usually people just say however they learned it, and that's fine. But I say tuple. So when I refer to tuples, that's how I say them. All right, if you've heard both, or if you've heard the other one. Ultimately, it's similar to a list. It is also an ordered collection of Python values. Theoretically, you can put whatever you want inside a tuple as well. Integer, float, string, Boolean, list, other tuple, whatever, is completely valid. The difference between the two is what we call mutability. When you create a list, it has a ton of methods that exist. You can use the methods to change the list, to add to it, delete from it, sort it, do whatever you want. Whereas the tuple is immutable, which means once we create a tuple, we cannot edit or rearrange that one tuple. It's set in stone. All right. The only way we can really manipulate it is to create a copy of it that has some change and then work with that. So when you create one, right, they're both the same in that they're an ordered collection of different elements, but that's kind of where the tuples functionality stops. They're usually used to sort of preserve the data inside, from like a safety perspective generally. Not always, but generally. So this is kind of where tuples end, but they're again very similar otherwise to lists, so we're going to mention them together at least. They can also hold again whatever types we want in combination together. The tuple though here only has numbers because I'm going to reference it later using just numbers, so I'm trying to make that work. Otherwise though, we can look at these and continue on and learn a little bit about mostly lists, but a little tuples. Anyone really quickly in the chat see an issue with the fact that tuples are defined with parentheses? A weird syntax issue we could run into theoretically in Python. Any ideas? Where have we already used parentheses? Any ideas? Where have we used parentheses already in Python, aside from function calls? Any ideas? What might get confusing to the user in using two parentheses to create a tuple, not necessarily the way we've done it, but more simply? No takers? All right. Well, we talked yesterday. When I say yesterday, I mean Tuesday. We talked Tuesday about the fact that in addition to using mathematical order of operations, we can use parentheses to group expressions together so they evaluate, which means that if we try to find the type of this, what do you think it's going to be? Right, this should be a tuple of one element, probably. Actually, I'll do this in 2 steps. So just to be clear, right, this is Python's built-in type function that tells us the type of its input with parentheses around the integer 4, right? This may or may not be a tuple of one element, 4. What type do we think this is going to be? Do we think it's going to be a tuple? Do we think it's going to be something that's not a tuple? On line 32. Any ideas what it's going to print on line 34? No takers. All right, it's quiet night. All right. So here we get an integer, and this is where the issue with a tuple lies. All right. If we have multiple elements, Python picks up on the commas. It knows it's a tuple. It's fine. If we have a single element, Python assumes this is an expression of just the integer 4, right? Which is the same as just typing 4, but we grouped it with parentheses for no real reason. To define a tuple of a single element, we actually have to add a trailing comma to that one element, and then we will be able to have it correctly become a tuple. And Python will infer it again from the trailing comma. It looks kind of strange, and it looks honestly to some people just kind of annoying. I don't like it, but it is the one way that we can, with just parentheses, create a single element tuple if we need to. There is, like we saw yesterday, just like with all the other types we saw, there is a function built into Python that will construct a tuple for us. It is just tuple parentheses. So we can use this with like tuple 4 to repurpose what we did above. If we don't like the trailing comma syntax, either one works. All right. But it's worth looking at this real quickly so we don't get confused with single element expression versus single element tuple. All right. Otherwise, we've said elements, right, are organized positionally and can be accessed positionally in a list or a tuple. And so the syntax to get them back is, for us, honestly, pretty easy. We have a list, like this said, our list up here. We can actually just access elements using the variable name followed by square brackets and then the name or the position of the element, right? So for example, 3. So if I print our list index 3, what do you guys think I'm going to get back from our print statement on line 39? Any ideas? Cool, we got an instant response in the chat. Someone's awake, that's fantastic. Otherwise, if I run this, we actually get 4, which is a weird behavior, not expected if you don't know to expect it. Technically, in Python, as well as most other programming languages, collections like the list type are actually 0 indexed, which means for whatever reason, the first element is going to be element 0. Everything after that is element like number -1. So this is element 0, this is element 1, this is element 2, element 3. So the element at index position 3 was actually 4, which is a weird behavior. Once you know it, you'll get used to it pretty quickly, I promise. Anyway, here we have, right, print our list index 0, and we do get back just 1, right? The integer 1, the first element in our list. We can do this with any element, right? Any index position, although if we give one that doesn't exist, we'll get a Python exception, right? This index error. So the index position does have to exist in our list, but otherwise, there's a few other, nice ways we can play with this notation, make it a little bit fancier. We can always use, again, single positions to get a single element, but there's a few shortcuts, right? If I don't know the length of my element of my list, I can use index -1. This will get me the last element, right? No matter what its length is, index position -1 is always going to go to the end and get that last element for me. In addition, if I don't want just one element, but I want some section of my list, we can start adding a few additional parameters to the brackets, right? To this indexing or slicing syntax. So to get a slice, which is what we call in Python a section of our list, there's a few different ways we can start. If I want to start at a position and get everything till the end, you just use a colon. And the colon basically divides two different inputs, a start and a stop. So 3 colon simply starts at 3 and gets us the rest of our list, right? So starting at index position 3, which is the element 4, we'll just continue on to the end. If we don't specify the end, we just go to the end of the list and then we're done. All right, so add some quick notes here. Access first element. This is, we can access last element. And here we can access every element from index position 3 to the end. Again, if we want to specify a stop, we can always just give us a stop, right? I can say 3 to 5. And this gives us starting at index position 3 up until but not including index position 5, right? So I get elements at index positions 3 and 4. Notice that the string 6 isn't there, so we stop non-inclusively at 5 to index position 5. I know it's kind of wordy, but I keep writing index position just because you know, it's not the 3rd element or the 5th element, it's the element at index 3, which is the 4th element. Alternatively, if I want to just get all of the elements up to a certain point from the beginning, right? If I specify no start, Python will make the assumption that we'll start at the beginning. So this will start at the beginning of our list, give me the subset of our list that is every element from the beginning up until, but not including the element at index position 5. So this is start to index position 5. There is an optional 3rd argument, right, to our slicing syntax if we want it. If we had a 2nd colon, so I'll just start with 1, and then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, so that's everything. The 3rd argument ends up being our step or our increment, all right, depending on who you ask. The increment is simply how many elements you skip in your slice. The default is 1. If I put a 2 here, what does anyone think? What am I going to get back from this statement on line 44? Any ideas? Which elements might I get back from our list? One, 2, 5, 7.1. 2, 4, 6. Cool. So we're thinking along the right track. But ultimately, we're going to get back 2, 4, 6 and false. Right? So we're going to start at the element at index position 1, which is 2. It's going to be able to skip and iterate every 2nd element instead of every 1, right? So we'll skip 2 elements, we'll get 4, 2 elements get 6, 2 elements get false. All right, so I will get that every other element subset. I could specify a 3 here instead. Oops. Get rid of these 2 arguments and then get every 3rd element, right? Starting with 1, the first one, and then going to 4, and then going to 7.1, and then that's it. All right, so you can customize these, 3 different inputs to get the exact subset of the list you want. This one is obviously kind of rarely used, but could be useful depending on the circumstances. So I will here just say every third element. So that's how we can access elements in our lists, right? Which is useful, right? We have a container, it can hold things, but what else can we do with it? So the next Python behavior we're actually going to look at here is a new concept we're going to call iteration, right? Iteration is a little bit weird at first, but the idea behind iteration is this. At face value, iteration is just the ability to run a block of code multiple times. All right, so iteration is a functionality that lets you just take some bit of code and execute it more than once if you would like, depending on some set criteria, obviously, right? Like I might want to do this action once for each item in our list, or 6 times or whatever, right? Without copying and pasting the code 6 times, right? Or some dynamic number of times we don't know. Alternatively, right, you might have to prompt the user for an input multiple times until they put in something that is spelled correctly or the right type, or something of that nature. We're going to look today at 2 different ways Python implements iteration for us. The first one we're going to be looking at is probably the most basic, which is iteration using for. All right. So Python has a for keyword, which lets us execute its associated code block a certain number of times. The way for works, and it's much easier to see it run, and then you'll kind of get the gist of it. We can just say, all right, for value in our list. The way for works is for will create some new variable name we don't have yet. And then afterward, it takes like some collection of things in Python, right? Here it's our list. It could be a string. It could be a tuple. Technically anything in Python that's what we call an iterator. For our purposes, we're going to just look at the fact that it could be a list or a tuple or a string for now. There's a lot of other slightly different things that technically count. We'll see one in a second that's like built in, but just think for now we have a collection of a certain number of things. We want to perform an action for each element. All right, so for value in our list. And then inside the indented code, each different value in this collection is going to, in sequence, be assigned to this variable. And then we'll run this code once, and then we'll jump back, we'll run it again, which means that the effect we get from these 2 lines is this, right? For each value in our list, we'll print that value. So we get 8 values printed to my terminal. And it's a little confusing at first, but the idea is, theoretically, when the for loop starts, we say, all right, we have a list. We've got a new variable name. Cool. We're going to take the first element in our list, which happens to be 1. We're going to assign 1 to this value. And then we're going to run this code. And then when we're done, right, when Python sees that we have no longer indented, but we're either at the end of our file or unindented somewhere, we'll say, all right, next. Right, next value in our list, 2, we're going to assign that to the value name, and then run this code again. We'll do that until we get to the end of our list. Python runs out of values, and we will break out of the loop and continue on. All right. this code can do whatever we want. Technically, it doesn't have to reference this value. It can just like do anything, right? And sometimes for loops are just used to execute any code a certain number of times, right? We can add 3 and 10 if we want this number of times, right? 8 times the number of elements in our list. There's usually just a little less utility for that. But it's worth noting that technically there's no built-in constraint that says like we need to reference value in here. But frequently we will. Cool. There's a lot of different ways we can, use iteration to our advantage. We'll see one in a second. But it is worth knowing before we get to these examples. In Python, there's a lot of good built-in functionality, right? So common problems we probably don't need to implement on our own. And when I say common problems, I mean things like calculating a sum of a bunch of at least numbers, or calculating a length, right? These are usually built into Python. So if we ever think like, I got a collection of elements, I need to do this really basic sum task, right? Odds are it may exist in the language. It might be worth looking that up. Right, if I run this, whoops. We don't want our tuple. We instead want, I'll go with, oh, that's fair actually. I use the same name in 2 places. Again, in Python, that's a no-no. We'll just overwrite it. There we go. We get here 22.1. Fantastic. Length 6. Cool. Number of elements in it is 6. 22.1, to me, that looks about correct. We can, right, as we can see, Python uses iteration behind the scenes there. The error mentioned it, but we can also implement these if we want with a simple for loop. For example, if I wanted to make a sum, right, this might be a good place where you can say, all right, if I want a sum, I really want to take each element in our tuple and I want to add them together and then get back some value. Right, that's a piece of code we could run multiple times. One way we can do that, right, we can create a variable called counter, initialize it to 0 because we don't have a sum yet, and then just say for elements in our tuple. Right, so each iteration elements will be each element starting at 1 and going up to 7.1. We can think, all right, I guess we want to take element and just add it to counter, and then add the next one to counter, add the next one to counter until counter has received the value of every element. It should at the end be like 22.1. All right, so we can just say cool counter equals counter plus element. Exactly in the chat. Cool. It is worth noting, by the way, I usually do put a space between all the operators and their operands in Python. That is conventional just to make it easier to read stuff. So that I can see white space between each of these. It just, again, makes it a little easier on the eyes. A lot of people don't, but it is considered, if you can do it, if you have space to do it, again, conventional for mathematical and assignment operators, right? Leave a space. If I want to, though, if I run this, right, this runs, we get back 22.1, which is awesome, right? So this code will behave the same as the sum function and create me a nice sum that I can use if I would like, all right? And adequately, again, iteratively add all these elements to this counter variable for me. I mentioned that there are a few occasional, other types built into Python that are what we call iterators, which means there's sort of a collection of things you can step through, is kind of like the English language definition for that, that aren't lists or tuples or strings, that are a little more niche. These are usually called generator functions. So what this is doing here, in Python there's built in this range generator, which will take an integer and it will basically create an iterable that contains all of the numbers, all the integers from 0 up until that number. So here, this is a long fancy way to say I generated all the numbers from 0 until the length of our list. Again, not inclusive, right? So there are 8 elements in our list, so I get back 0 through 7, right? Length range 8 gives me back all the numbers 0 through 7. So like indexing, it starts at 0 and ends at end minus 1. But you'll sometimes see this sort of pattern as well. For whatever reason, if you want to generate a list of index positions in an element instead of iterate through all the values, right? This is just the same as getting all the index positions in our list, starting at 0, going through 7. You'll occasionally see it. It's a little weird and a little bit roundabout usually, but it is doable. All right, and so you'll see it sometimes on the internet, so it's worth mentioning. Otherwise, but again, there are some other function calls you'll see in there that are generators that return you something that behaves like a list here, but it is not a list. Otherwise, this is what for-based iteration looks like. I'm going to quickly add the pass keyword here and add the pass keyword. I'll just comment a bunch of these out. I'll send you the link to this file afterwards, so you can make your own copy and play around with it. You can always get rid of the $signs, get rid of the comments for us. Whoops. So you can run stuff, but for our own sanity, I'm going to not keep printing all this stuff to my console. Python has, for that reason, a nice built-in keyword called pass, whose whole job is to take up space and do literally nothing. Pass is frequently used for code that is unfinished, because otherwise, to Python, colon with no associated code block or indentation is a syntax error, right? Python sees this for loop and says, Greg, you need to give me something in the for loop to do. I need that code block. Pass is frequently used to satisfy that condition. It won't do anything, but Python sees this indent and sees a thing and is cool with it. This is basically telling Python do nothing and just continue. All right. So this will now not give me a syntax error. Cool. So we just saw a for-based iteration, which is, it's a little weird when you start out with it, but it ultimately makes sense, right? We'll iterate this number of times, once for each thing in this collection of things, and then we will stop and continue on with our code. But sometimes you need to run some associated block of code, right? Depending on the use case, obviously, but sometimes we might need to run a code block some number of times that we can't predict beforehand. And this is where the while-based iteration in Python comes in, right? The while keyword and what we call a while loop. In Python, you'll hear the word loop. For and while are used in that context. A loop usually just refers to an iterative body of code, right? Some code that performs iteration. So you'll hear of for loops. That is the for statement plus its code block. You'll hear while loops, which is the while statement and line, and then its associated block of code, right? So when you hear loop, that just means iteration. The while loop, again, is just for when we need to iterate based on some condition that we may or may not know beforehand. I mean, we have to know it obviously, but we may or may not know like when we'll be done, right? This is based on a condition. We can't say we'll do this 6 times, we'll do this once. It could be as many times as you need until usually a user satisfies some criteria, right? Again, the example I gave before was prompting a user for something, right? A user might enter correct input the first time and be done with it. A user might never enter correct input because, they don't speak the language, or they just keep messing up the key. They don't know what they're doing. So we may need to iterate for an arbitrarily long amount of time. So for this while-based iteration, we set things up a little more carefully, right? So I'm going to create a brief while snippet of code. The way while works is while is always followed by a condition. This while loop, right? This while block of code will keep running until this condition is false, right? So if this condition is true, while will keep running. And if we look at this, we can see that I is initialized to be 0. 0 is less than 5, so this will run at least once. And usually we'll have, some logic at this point, right? Something in here, some associated block of code. Again, we use an indent for every line that's associated with while, so Python can figure it out. We're just going to print I, and then we're going to reassign I. We're going to add 1 to I, right? If you've not seen it before, the plus equals, the increment operator in Python is the same as, this is the same as saying I equals I plus 1. It will add 1 to the current value of I and then reassign that to I, right? So the first time this will make I 1. Second time this will make I 2. Our ultimate effect is that we will get 0, 1, 2, 3, 4, and then be done with it, because once I is equal to 4, right? Or we can start at the beginning, right? I is equal to 0. Is I less than 5? Yes. All right, so while says, cool. While 0 is less than 5 is, we'll print 0. We'll add 1, all right. I is 1. While 1 is less than 5, sure it is. We'll print 1. We'll keep going until I is 5. While 5 is less than 5, nope. We'll jump out, break out of the loop, and continue on with our script. Does anyone see an issue here? Potential issue, at least. Anyone? Potential issue with using while loops. For loop is great. It will iterate an exact number of times and then finish. How do I know a while loop will finish? Anyone? So the big issue here is that I really don't know a while loop will finish except by careful design, which isn't to say that we shouldn't use while loops, right? They're a different use case. We sometimes will need while loops theoretically, but we need to design a while loop carefully, because if I don't design it carefully, you have a problem. This while loop is always going to be true as it's currently designed. If I'm not careful, we get this. We get what's called an infinite loop, which is obviously not good, because this will, literally run until one of two things happens. Until someone notices, which if your code is in production, probably not going to happen. Or until it runs out of memory, I guess, which isn't ideal either, right? It's going to take a long time to find an integer that will cause me memory issues. So hopefully someone will notice the code is not doing what it's supposed to, or it's stuck, or it's hanging. But a lot of the time that's running in the background somewhere and people might not notice for a while. Which is to say, if we use while loops, we want to be very careful with them. And just make sure we design them so they will, in fact, definitely terminate at some point. All right, I'll stop the anxiety-inducing while loop going. But I hope we get the idea. Right, while loops only work because we have made sure they will work. So I'm going to rewrite this so it works correctly in the future. There we go. But it's worth thinking of that, right? There's a possibly apocryphal story, but apparently not. I have a current full-time bootcamp student who is from Houston, and he has told me, but apparently there, because there's a lot of NASA there, it is actually a well-known fact, and it's like, seems to be true, that at NASA, they apparently don't let you put while loops in your code. So if you deploy code to space with a while loop that doesn't terminate correctly or has some edge case you haven't taken into account, you can't really do anything about it, right? You've wasted billions of dollars. So allegedly, at least, in NASA, you're not allowed to use while loops. They find other ways around stuff, which again isn't to say don't use while loops. There's a time and place for them sometimes, but just be careful, all right? This is one implementation of a while loop, right? We have a condition, we will iterate till said condition is met. Technically, we can implement while loops differently if we want to. This might be an issue, right? What's wrong with this while loop? Anyone, what's wrong with this while loop here on line 72? This is an infinite loop, right? Because, I mean, true is not even an expression. True is like a value. I can't reassign true. So this is going to run forever, right? While true, every time the while loop will just be like, while, all right, cool, it's still true. I'll keep going forever. There is a built-in keyword we can use here, though. This is a rewriting of the original while loop here. Built into Python, if you want to interrupt a loop's execution, right, or break out of the loop, there is a built-in break keyword, which we can use to explicitly tell Python, right, find your nearest loop, stop, and then we'll continue on with our code. Right, so break will actually tell Python to literally find its closest loop and terminate its execution. Wrong condition. There we go. So here we get basically the same effect. Technically, this is greater than 5, right? And the print comes first, so we'll get one extra number printed. If you want the same effect, we could do this. Quick note, by the way, right? We have an if inside a while. If still gets its own indentation for the break statement associated with it. So every time we need to associate code, we can keep indenting and moving stuff across so that Python still sees this implicit association, just like it will see this association. All right. Obviously, we try not to use too many indented code blocks in a row because our code slowly migrates across the screen and becomes hard to look at. But sometimes you do need to do something like this, which is completely acceptable. All right. Cool. Any questions? If not, we're going to look at one. Cool. We got an actual no. No one ever says no, so props to you for telling me you don't have questions. People just don't respond usually either way. Getting people to type in the chat is just a little too much effort sometimes. But if not, we're going to jump to one last topic for today. That's going to be another type of control flow, kind of like we saw before, right? With the if else control flow, just to get a little more practice, see another way we can control how our code executes, but also put all of these different concepts together. All right, so we're gonna look at control flow based on exceptions. This is a weird idea to some people, right? We've seen Python exceptions at least once earlier, right, with an index error. But sometimes in Python, you're okay with some exceptions happening, right? Again, when I say exception, that's Python's internal representation of an error. But sometimes in Python, you're okay with exceptions happening, or certain types of exception might be expected. It's easier to just tell Python, hey, this might happen, that's fine. In that case, do this, right? Or do something else. We can control how our code executes based on presence or absence of an exception, or what type of exception it was specifically. An example is going to be, we're first going to create a new tuple. We're a little far from the other ones, so we'll wait. So we're going to 100. Just get a bunch of numbers, 76, 0, 124, 812, 2, 4, 2, and then we'll get a string, right? So we get a bunch of 3 different types, all of which are numbers except the string, right? Numbers varying from 0 to slightly over 8,000. Cool. Obviously, we can iterate through our tuple if we want, right? For num in new tuple. And notice I'm calling, I'm naming this variable num, right? So we're expecting mostly numbers here. This is for the reader to know, like, hey, this is full of numbers. Just print num, right? Again, this is for loop execution, right? We should get each different element in a row, which we do, 1 through string, all in the correct order. Let's say we want to divide these, right? We want to, for some arbitrary reason, we want to see what the answer is here, right? How many times does each number go into 1,000? It's an important, it's an important task coming from the bosses, I guess. But we have an issue here. Our data is not always going to be perfect, as is true with all data ever in the world anywhere. We might not always be able to say, right, there won't be a 0 in our data, because if you look over here, we got a 0 division error, which will succinctly tell me the issue is division by 0, right? We can't divide by 0. It's not mathematically possible. Python will not let me do it. But let's say for a second, right, we may actually have a situation where there may be zeros in our data. It's just the way it is, right? We can use a different type of control flow in Python, and we can use the try statement and the except statement. All right. So the way these work, relatively straightforward. It sounds kind of like, I mean, they work the way they sound. Try simply takes a line of code and basically tells Python to attempt it, or not one, but a block of code, right? Whatever is indented underneath the try statement. Python will do its best to execute it line by line until it encounters an exception. When it encounters an exception, instead of jumping straight to the halting execution and showing me this over here, we will instead jump to whatever is underneath this except block and just run that code instead, right? For example, print. Let's print an error occurred, right? If I run this now, you see our code happens correctly, right? We got 1,000, makes sense, 10, 13, right? We got an error occurred. So when we hit 0, instead of raising an exception, Python would just ran this code. It's worth noting, by the way, every try does need an except. You can't have try without excepts. You can have if without else, but this is different, right? We need to know what to do when there's an exception, or there's no point in trying this. And we'll see we actually got two errors, right? One for 0 and one if we look at the end for a string, which makes sense, right? 1,000 divided by a string doesn't make any sense. If we want, we can move on a little bit further, and instead of just giving a global except, we can be a little more specific. Why might I want to be a little more specific than just saying except? Any ideas? What more information might I want to know? Anyone? Yeah, Marcus, that kind of makes sense. Why the error occurred? Usually, realistically, I wish Python could tell us why the errors occur, but that's just not usually the case. So you can't get the why. The why is a like figure out what type of error it was and figure it out scenario. But we could figure out what type of error it was, right? Which kind of helps, right? Which is kind of what you're getting at too, right? What happened? Because these are different types of error, right? This is a 0 division error, and this here is actually going to be a type error. So except can optionally take some little argument afterwards, right? An exception type. So I'm going to type out 0 division error. It turned green, which means I spelled it right. Now when I run this, I get a different behavior, right? In the instance of a 0 division error, we printed this. In the instance of a type error, we didn't have any code to handle for a type error, and thus Python just raised the exception and halted execution in my console, which is possibly a desired behavior. I don't want to just mask all errors, right? Some of them are not errors we want. I need this to happen so I can figure out what the heck happened and debug it and fix my code. With just a global except that just says except, I never know what the errors are or if they're happening, because my code will just keep chugging along without properly alerting me. All right. We can also, if we want, have multiple excepts for each different type of error we want to allow. And then this way we can run code in a 0 division error or a type error scenario that's different. Also, if we have a third error type pop up, we can handle that in its own unique way as well. In the instance of a type error here, for now, I'll just print string was found. But in the instance of 0, I'll actually just print 0, right? And pretend we have some data-related reason that this is fine. So now I've sort of fully customized the behavior of my code so that I get either some output that might make more sense or a more custom message or notification that the error occurred. All right. So now we can start putting all these together, right, to make code that is more useful and also just more helpful to the user and developer, which is nice. Any questions about any of this stuff we've been through today? If not, I'm going to quickly in the chat here send. This is the link to the file I was working in today as some notes. Please, feel free to visit it, make your own copy, play around with it if you would like. You will also, as a follow-up to today, get that link again in again a less ephemeral capacity than the Zoom chat, which does disappear the minute I close the call. But you'll also get the that same link. You will get another link to I think Python, the reference that I linked earlier in the call, right? This guy here. Let's see, how many error types are there? Do I have a list of error types? Ooh, shit, there are There are a lot. This is not a like can list them all from memory type deal. This is like a there are so many, I'm not sure I'd be able to find a comprehensive list quickly or easily, or that like someone's bothered to curate it. I'm sure someone has, but like finding it's going to be a challenge. Honestly, this isn't something to memorize really. If you write Python, one of the best ways to know errors is to simply write code, get an exception, figure out why, and then do this after the fact. There are possibly hundreds of different error classes in Python. There's some really specific ones um, related to all sorts of things. They try to be customizable so that the error message you get is relatively understandable of like what happened and why. Yeah. So I would say over 100 certainly, if not multiple hundred, depending on I don't have a count, but I don't know if there's a good list, honestly. Unfortunately, does that kind of answer your question anyway, though? They're very much a like if you encounter them as you write your code, you'll get to know some of the common ones. But I would say just the way to learn them is just keep writing code, and you'll see the common ones anyway. But there's also not too much utility to like memorizing them. Um, yeah, does that answer your question enough? Hopefully. Um, I'll after the call, I'll try to look for like a comprehensive error list. If I find one, I'll send it on Discord or something. But I don't find it likely. All right. Otherwise, any other questions? No problem. If not, again, if not, you'll get these resources and links via a follow-up email at some point relatively soon. So you'll have that again in easily referenceable fashion. So you'll get all these links anyway. I'm going to leave the call open for another minute or so. Anyway, I'll mute myself, but leave it open just so that you can pull this stuff out of the chat if you would like to. Start reading it and looking at it quickly. If not, though, I'll just, I want to thank you guys for coming back for day 2 of Intro to Python. In the exercise link is still what it is. You'll get that re-upping in the email as well. The invite link, I don't have that one off the top of my head, so I can't just send it right now. But anyway, thanks for coming. We'll be back on the same link, same time on Tuesday. You get a few days off from hearing me talk. A little time to practice Python, hopefully. Otherwise, again, thanks for coming, and I'll see you guys back here on Tuesday.